Hello and welcome. So, have you ever stopped to think about what happens in that tiny, tiny fraction of a second when sunlight actually hits the Earth? It seems like such a simple thing, right? But that single moment, well, it's the engine that drives our entire planet's climate. Let's really get into it.
Okay, let's start with something we've all felt. Picture a hot summer day. You can walk on the light-colored sand at the beach pretty comfortably, right? But the moment you step onto that dark asphalt road, ouch, you're hopping around because it is scorching hot. Why is that? That very simple difference holds the key to understanding how our entire world warms up and cools down. You see, sunlight is pure energy. And when that energy hits any surface here on our planet, it can't just disappear. Basic physics tells us it has to go somewhere. And it turns out there are really only 3 paths it can take. And that's it. Those are the only 3 options. Every single ray of light is either going to bounce off, get soaked in, or pass straight through. This simple, instantaneous choice, reflect, absorb, or transmit, is what decides if a surface gets hot or stays cool. And it's happening billions of times a second all over the globe. Now, for most of the solid stuff we see every day, the ground, buildings, thick forests, light can't really pass through them. So for these opaque surfaces, the story gets even simpler. It just boils down to a two-way battle, reflection versus absorption. Is the energy going to bounce away or is it going to soak in?
So, what is it that decides the winner of this battle? How does a surface choose whether to reflect light or to absorb it? Well, the answer lies in a property with a really cool name. It's called albedo. Albedo is just a fancy word for how reflective a surface is. That's all. A high albedo means it reflects a lot, and so it stays cooler. A low albedo means it doesn't reflect much, so it must be absorbing the rest, and it heats up. It's actually that straightforward. And this analogy makes it perfectly clear. A high albedo surface, like fresh white snow, is basically a mirror. It just bounces most of the sun's energy straight back into space and stays nice and cool. But a low albedo surface, like that dark asphalt we talked about, it's more like a sponge. It just soaks up all that energy and gets incredibly hot.
And just look at this chart. The difference is actually dramatic. On the left, you've got fresh snow. It reflects up to 90% of sunlight. Now compare that to asphalt at the bottom. It reflects less than 10%. It is a total energy sponge. And this, right here, is exactly why that road burns your feet and the sand doesn't. Okay, so let's zoom out a bit and see how this whole thing plays out on a global scale. We're going to take a quick tour around the world to see albedo in action, from the icy poles all the way to the tropics. So, at the poles, you've got the planet's amazing white ice caps. They are like giant mirrors for the Earth, reflecting sunlight back out and acting as a natural air conditioner. But then, on the other hand, you have our vast, dark oceans. They are the ultimate energy sponges, absorbing and storing just enormous amounts of the sun's heat. But wait, albedo isn't the only thing that matters. A dark forest, for example, absorbs a ton of light, so you'd think it will be super hot. But forests have a secret weapon. They sweat. Through a process called transpiration, trees release water vapor, which actually cools the air around them. A brighter desert reflects more light, but because there's no water for this evaporative cooling, it gets intensely hot. So the big takeaway here is that moisture is a complete game changer. When a surface is wet, the sun's energy gets busy evaporating that water instead of just heating the ground. That absorbed energy has a job to do, turning liquid into vapor, so it can't raise the temperature as much. It's like nature's own built-in air conditioning system. And what is truly incredible is that these different energy signatures, these different ways surfaces handle light and heat, are so distinct that we can see them clearly all the way from space. Satellites can literally read the Earth's surface like an open book from hundreds of kilometers up. And the way they do this is by looking at something called a spectral signature. Now, it sounds complicated, but just think of it like a fingerprint. Every single surface on Earth, a leaf, a bit of water, a patch of soil, it reflects a unique combination of light colors or wavelengths. And that unique pattern, that's its fingerprint. So by reading these light fingerprints, satellites can map our entire world with incredible detail. For instance, healthy plants are super bright in a type of light our eyes can't even see, called near-infrared. Water, on the other hand, just absorbs this light, so it looks very dark to a satellite. We can even measure the heat radiating off a surface to take its temperature from orbit. It's amazing. So, we've gone from a single ray of sunlight all the way up to a satellite's view of the whole planet. Now, let's connect all of these dots to the biggest story of all, our global climate.
This brings us to a really critical and, frankly, a pretty dangerous process in climate science. It's called the ice albedo feedback loop, and it's a vicious cycle. It starts like this. As the planet warms, the reflective white ice starts to melt. This exposes the dark, absorbent ocean underneath. That dark surface then soaks up way more solar energy, which causes, you guessed it, even more warming, which then melts even more ice. And the cycle just keeps going, getting faster and faster.
And this isn't just some abstract theory in a textbook. This is happening right now, as we speak. This dangerous feedback loop is one of the main reasons why the Arctic is warming up so much faster than the rest of the planet. Basically, the Earth's giant polar mirror is shrinking, and its heat sponge is growing.
Now let's bring all of this science right back down to our own backyards. Have you ever noticed how a big city can feel like an oven on a summer night, way hotter than the countryside just a few kilometers away? Well, that's a real thing. It's called the urban heat island effect.
And the reasons for it are exactly what we've been talking about. Our cities are just covered in low albedo surfaces, dark asphalt roads, dark roofs that soak up sunlight all day long. Then materials like concrete and brick, they act like thermal batteries, storing all that heat and then releasing it slowly through the night. And on top of that, there are fewer trees and parks, which means we lose that vital evaporative cooling we talked about.
All right, so what's the bottom line here? What should you take away from all this? First, the ground beneath our feet isn't passive. It's actively managing the sun's energy. Second, albedo, that measure of reflectivity, is like a master switch that controls whether a surface heats up or stays cool. Third, this means the materials we choose to build our cities with have real, direct consequences for our local environment. And finally, understanding this science is exactly how we keep an eye on the health of our entire planet from space.
And all of this leaves us with a really crucial question for the future. We now know for a fact that the surfaces we build can either help cool our world or, well, cook it. So with that knowledge, how should we be designing the cities of tomorrow? How can we make them work with our climate instead of against it? What should they even look like? It's something we all really need to think about. Thanks for joining me for this explainer.